So this is another question related to the statistical process control, which we covered in our very last session. And I'll try to touch upon on every concept that on possible questions that could be asked in MCQs, objective type of questions. So the idea of the idea of doing such questions is to take one problem and try to look at it in every possible dimension, and each dimension could be a separate question when it comes to a format where you will be tested on objective like MCQs type of questions. So let's start with this question, and this question is about a bank is setting up control charts to monitor the time between a customer reporting a credit card lost or stolen and receiving a replacement credit card, right? So they are monitoring the time. Third random sample of size 30 random samples of size 6 were taken at the bank's central loss and theft reporting center each per day. So what's happening here? They have a sample, so total number of samples that they took are 30. And in every sample that they're taking, they're taking six, individuals or reports of credit card replacements, right? And if you just read this line, there's one very important fact which is given in the statement, which is the sample time, like how often we are taking our samples, right? And we are taking our samples each day, after one day, after 24 hours, right? So this is like one of the insight that we can get by reading this line. 30 number of samples is very clear, the sample size is very clear, but there's one other important thing, that was sample, how often we're taking sample. We're taking sample on daily basis. So after each day, I'm taking my sample. So if I just tell you, if I had to find my ATS, average time to signal, whose formula is ARL into how often I'm taking the sample. So in this case, let's say I'm just assuming hypothetically, if my ARL is 30 and I'm taking sample after one day, so 30 into 1 would be 30. So my ATS, average time to signal, would be 30. But that's just for an example, for the understanding point of view. Now you're given with the table. Um, so this is my table, which the first row is the first row are the number of samples. So 1 till 30th. So starting from here, 1, 2, 3, 4, 5, 6. So these are the sample numbers. And then corresponding to each sample, I'm given with the mean. And what does this mean? This mean is the time, the number of days taken when when any person reported that his card is lost or stolen, and the time he got a new one. So the mean for the first sample, and in the first sample they took six different cases, and the mean time was 6.167, right? And similarly, I'm given the mean for the rest of the 30 samples. And the range would be, let's say, if my first sample, I had six people, my first person got my first person got who reported that his credit card lost, got his new one in 4 days. And maybe my sixth person who reported, he got card after 7 days. So this was the highest number, and this was the lowest number of days taken in that one single sample. I'm just talking about the first sample. You'll go into the first sample and you'll see what is the highest number of days being taken and what is the lowest number of days being taken. So the range formula is max minus min, right? So you'll subtract to get the range. So this range is for every sample is given to you. So whatever the highest number, whatever the maximum number of days in the first sample was, and whatever the minimum number of days was in the first sample, you subtract them and you get the range. Similarly, I'm given the ranges for the rest of the samples up until 30th samples. So this is the kind of information that you would be given, right? And then other important thing that you would be given would be the mean of sample means. So I'm given with the sample means, right? So 6.167, 6.333, 4.333. These are the mean sample means of the corresponding sample. So if I talk about, if I, let's say, take sample number 16, the sample mean for the sample number 16 is 4.333. But what I need when I'll be finding the control limits, I need the mean of the sample means, right? I need the mean of the samples means. And if you like refer it to your module, they were calling it X bar bar. So your X bar bar is 5.6333. And I'm writing its formula because we will be using this formula down the line while solving this question. What would be the formula for the X bar bar? The formula of the X bar bar would be the sum of all the means. And remember this formula because we would be using this formula down in few of the parts of this question. Sum of all the sample means, let's call it sample means. And how many total number of samples do we have? We have 30 samples, right? So divided by 30. And similarly, I am given with the mean of the sample range, right? I have range for each sample, 4, 4, 5, 3, basically the third row, this one. I have 30 such ranges for each sample. So similarly, I can find the average of the ranges. So I'll take the sum of all sample ranges. I'll take the sum of all sample ranges and divide them by 30. So this is how I'll get my R bar. So in this case, this my X bar bar is 5.633 and my R bar is 3.833. So this is what we already have given. So until now, we understood what means what, like what do we mean by X bar bar? What do we mean by R bar? What is how often we are taking our sample size, how often we are taking our samples, what is our sample size, and the information that we are given with. Now let's move forward and solve our first part of this question. What is our first part? Calculate the preliminary limits for the X bar chart. And the B part, I'm solving the A and B simultaneously, right? What do we mean by preliminary? So here we need to understand the difference between the preliminary limits and the working control limits. And the difference is very simple. This table, the data table that you're given, I'm referring it as a table one. I'm calling it T1. This is your table one. These 30 samples are the samples that you went into the process and you randomly picked 30 samples, and each sample were the size of 6, right? And you measured the sample mean and you measured the range corresponding to each sample. Now, to to calculate the limits, you only need the X bar bar and R bar. That's all you need, right? But the fact is the preliminary limits would solely be derived or be calculated on the basis of what you observed. So this T1 is your observed data, right? So you would use X bar bar as 5.633 and your R bar 3.833 because these two values are being computed on the observed data. But that wouldn't be the same for the working control limits because when we are calculating the working control limits in these 30 samples, there is a possibility that some samples would be either above or below the control limits, right? So once I like calculate the let's solve the first part, and my formula for the limits, my formula for the control limits, I'm calling it control limits. Now it could be lower and upper. My formula for the control limits is X bar bar plus A2 R bar. Now, because I'm not given with the standard deviation, so I would rather use A2 here. So this is one of the formula to find the control limits for X bar chart. Note it down, please. Like you need to remember these formulas, and I'll make a table and share it with you guys. To depending upon the situation, you would have to pick the right formula. Now here, because I'm not given with the standard deviation, so I'm not going to use this formula. Like we have studied this formula, right? But since because I do not have the sigma, which is the standard deviation, so that's why I would rather use the A2. Answer, you would get the same answer, but depending upon the situation, depending upon the data I'm given with, I'll have to choose my formula accordingly. Now the UCL, so let's my X bar bar is 5.666, which is this, and let's calculate A2 R bar. Now, what would be my A2? What is my sample size? My sample size is 6. I'll go to this table and my sample size is 6 and my A2 is 0. So this value, right? So my A2 is 0.483 multiplied by what is my R bar? My R bar is 3.833. 3.833 multiplied by 0.483. I'm getting 1.85, like approximately 1.85 up to 2 decimal places. So my upper control limit would be 5 point. So now this 5.6 is coming from the observed data. This is the mean of the sample means of these 30 samples. So 5.633 plus 1.85, and my lower control limit would be 5.633 minus 1.85. So this is how I would get my 5.633. 7.48 is my upper control limit, and my lower control limit would be 5.633 minus 1.85, and that is 3.78. Now, these are your preliminary limits. These are known as preliminary limits. The fact that these are being calculated on your sample data, on your observed data. And now in the B part, I need to find the working control limits. Once I'm given with the upper control limit and the lower control limit, I'll go back to my observed data, and comparing to these two limits, I'll see if any of my sample is out of control. So if I look at my first sample in the observed data, what is the mean for the first sample? The mean for the first sample is 6.167. Now 6.167, I'll come back to my preliminary limits and I'll see where 6.167 lies. It is neither below control limit or neither below lower control limit or above upper control limit. So it's technically between the interval between LCL and UCL. So this the first sample is under our control. Similarly, the second is under our control. The third is are under our control because it's between the interval of 3.78 and 7.48, right? It's neither below the lower control limit or above the upper control limit. And in such a manner, you would compare all these 30 samples. And only 28 sample is out of control because its mean is 8.00. So now 8.00 is above the upper control limit. Our upper control limit for the preliminary is 7.48, but for the 28th sample, my mean is 8.000. So it's above the upper control limit. So my 28 sample is out of control. Rest of the samples are under control. Now to find the working control limits, what I'll do, I'll take away the mean, which is 8.000 from the X bar bar, and I'll similarly take away 2, which is the range for this particular. So idea is I'll subtract this sample out of my control limits calculation. So this is the whole goal. And I we have went through in while solving or while like covering the module, but that wasn't like a like a good question, like because we were understanding the intuitions and all. So now here you see a structured question. So before we find the working control limit, I'll kick out this sample out of my calculations. And what it do? It will change my X bar bar, and it'll change my R bar by a like little value, but it will change, right? Let's see how it will change. Now, you can't really go back and like to the one way or the longer way to solve this question is that you take the sum of all the means except 28. So now you would have like how many samples you would left with because you're kicking out the 28 sample. The number of samples you would left with what? For the B part, number of samples you would left with would be 29 because you have kicked out the 28 sample. Now you're left with the 29 samples total. The count would be 29. The sample size is 6 still. The one way is to take the sum of all the means except 28 and then divide it by 28 to get the X bar part, right? Because this is the formula to find the X bar part, right? And similarly for the R bar, this is the formula. You take the sum of all the ranges except 28 and you divide it by 29, you will get the range. And other way is that what you can do is what would be the sum of if our X bar. So if I like look at this formula, my formula was sum divided by 30 was equals to 5.633, right? I can calculate the sum because I don't want to do this hectic calculation of like adding them up. What I can do is I can calculate my sum quickly. I can multiply this 5.633 into 30. Now I'll get the sum. What will be my sum? 5.633 multiplied by 30. And I'm doing it by using the formula. There is no like difficulty. Like it's quite simple. It's sum. 30 was dividing it here. I take it to the right side and multiply it with the sample mean, the mean of the sample means, which is 5.633. So it will give me the sum of all these 30, the mean of these 30 samples, which is 1.68 or 168.99. So this sum also include the 28, the mean of the 28 sample, right? Because this is for the 30 samples. Now what I can do is to find the sum of rest of the 29 sample. And which sample we're kicking out? We're kicking out sample number 28. I can subtract from the total sum of all means, I can subtract the mean of the 28 sample. I can do this. And I'll get 160.9. Now, this is the sum of the 29 sample except 28. So if I had to calculate my new X bar, what it would be? Now I have a sum for the rest of the 129 samples, which is 160.99. And what is the formula for the average? Sum upon the total number of samples. But here, my total number of samples are 29, not 30, divided by 29. Now my X bar, my mean of the sample mean is 5.55. This is my sample mean. Similarly, I need to find my R bar, my updated R bar, because I need to kick out the 28 sample. The same, you need to do the same maths, and I'm doing it right here. My original R bar was 3.833. And how would I get this? I'll take the sum of all ranges of 30 sample, divide them by 30. I can get the sum. What would be my sum in this case? 3.833 multiplied by 30 equals to the sum of all ranges. Sum of all sample ranges. Sum of all sample ranges. So that would be multiplied by, 30. This is coming up as a sum of all sample ranges is equals to 114.99. So this is the sum for all the ranges. So if you add 4 plus 4 plus 5 plus 3 plus 5 Up until here, you would get 114.99 as your answer. But I need to find my updated, I need to kick out sample number 28. Now I'll go back and I'll see what is the range for the 28 sample. The range for the 28 sample is 2. So what I'll do here, I have the sum of all those 30. I'll, sorry, 0.99 minus 2. This minus 2 is the sample, is the range, the sample range for the 28 sample. I would get what? I'm getting 112.99. So this is my range for the rest of the 29 samples. Now I can find my new. So I'm calling this, I'm putting W here. This W stands for the working limit. So now, and this R bar is for the working range, right? For the working limits, updated, calculations. So now 112.99 divided by 29 would give me my updated R bar. And that would be 3 point. So this is 3.89, but I'm like writing it down as 3.9. So, or maybe let's write 3.89. So this is my new updated R bar. I hope like this is clear. Now you need to find the working control limit, the working control limit. And I'm pretty sure that you now understand what is the difference between the preliminary limits and working control limits. So there's just this difference between both. Now the formula is same, x bar bar plus A2 R bar. Sorry, it's R bar. Now, but here my x bar bar is not the previous one, not the original one. My x bar bar is 5.55. So x bar, basically W, I'm referring to this one, right? So this would be used here. And let's find our A2 R bar W. My A2 was same, 0.483 into what is my RW? RW is 3.89. So can we multiply it with, oh, sorry, 0.483? And I'm getting 1.88. 1.88. And now to find the working upper control limit, that would be 5.55 plus 1.88. And my lower control limit would be 5.55 minus 1.8. So this is how I would get my working control limits. I hope there is no confusion now. And let's complete our calculation. This happens to be 7.43. And the lower control limit happens to be 5.55 minus 1. So this is 3.67, right? So these are our working control limits, and you exactly know how we reached here. I'm erasing these calculations, and let's go to the third one. What is the third part? Explain how this chart will give signals that the variable time between a customer reporting so again the is out of statistical control. So we have a variable which is basically the time taken between the reporting time of the credit card and getting back a replacement card. So the time taken between these two processes is basically our variable that we are tracking. Okay, so how this chart will give signals that the variable is out of control. How does it happen? So if you take a sample, right? So you have your working. So by the way, these are the working limits that you put into system. So you follow these working limits now. These are your benchmarks against which you will assess each sample that you would be taking moving forward. So if you read the C part, when would you tell that your corresponding sample is out of control if it's out of control, right? And what do we mean by out of control sample? Out of control sample would be if someone went and if you took a sample and the sample mean happens to be either below lower control limit or above upper control limit. So your upper control limit, working upper control limit is 7.43. So if the mean for any corresponding sample, let's say, is 7.45, now it's above your upper control limit, you would say that this is out of control. This sample, whatever that sample is, this sample is out of control. Similarly, for the lower control limit, if it's, let's say, 3.3, the average how the average days happens to be 3, you would say that this is below lower control limit, and that is why it is out of control. So this is like theoretical answer and more intuitive. And let's move to the D part. Suppose an assignable cause of variation increases the mean to 6.5. How long on average would be taken before this assignable cause of variation is signaled on the X bar chart? Now, these questions, so look at these D and E part. So I'll tell you what these questions are about. These questions are about the ARL and the ETS, right? ARL and the ETS. ARL is the average run length, and ETS is the average time to signal. ARL and ETS are the same thing, but ETS tells you the time and ARL tells you the number of samples. The benchmark is same. If you have a process, how many samples it would take to signal out the variation. So you have like assigned a variation, right? You have assigned a cause of variation, which increased the mean to 6.5. So this is given to us, right? Our process has been changed. Now, because our process has been changed, how long would it take for the system that we built for the control limits for the working control limits it would take to signal out these changes and to track these because we have to measure it by some numbers, and those measuring tools are ARL and ETS. ARL tells us that how many samples it would take to signal this variation that is being assigned, and ATS would tell you how much time it would take to signal out this variation. So ATS is the formula for the ATS is very simple. The ARL into the how often you're taking your samples. And for this example, we are taking samples on daily basis. So after one day. So if I'm telling my ATS in days unit, whatever my ARL is, I'll multiply my ARL with the one. I'll get the ATS. But the more like complicated, like a little bit complicated calculation is for the ARL, because for the ARL I need my probability, right? And the because the formula to find the ARL is actually the reciprocal of the probability. And probability of what? Probability of, so let's say if this was my chart and this was my upper control limit. And by the way, because this is an increase in the mean, we are awfully like interested in the upward side, not the downward side. So I would be rather interested in the upper control limit, because see, if the mean was before was 5.6 and now it went up to 6.5, so that means the most of the values are gone up because my mean is increasing. And what is the formula for the mean? The formula for the mean is sum upon the number of samples. And if you look at this formula, how the mean can be increased? The mean can only be increased if you increase the sum. And how would the sum would increase? If you increase the values that are like gathering up to make that sum. So 5 plus 5 is 10 divided by 2, right? If you want to increase the sample, if you want to increase the mean, you would not increase the denominator, you would increase the numerator. And numerator is 5 plus 5. And if you make it 10 plus 10, you would get 20 divided by 2. Now your mean has increased to number 10, right? So if you're increasing your number, you're basically increasing your what? The values, which are like gathering up to make that sum. So I hope this is clear now. And let's do the calculation for the ARL and ETS like quite simple. Can you guys like calculate and see if you can find the z-score for this problem? Because see, to find the probability, I need the z-score. And once I have the z-score, I can go there and look in the table against my z-score value, and I'll check what? I'll check my, and let me just confirm one thing here. My z value would be, yes, exactly. Oh, sorry. What was my, so I'll use my working control limits, and that is 7 point, I'm writing it down here because I would need this in the formula, 3.67. So to find the z-score, what I can do? My UCL minus for the UCL, my z-score for the UCL and my z-score for the LCL. UCL, the working upper control limit minus the updated mean. Updated mean is 6.5, right? Divided by the standard deviation, or the standard, not standard deviation, but standard error. I would get my UCL. But how would I get my uh, standard error here? That's another calculation here now. Can I get my standard deviation here? Because this is my standard error. The formula to find the z-score is UCL minus the updated mean, which is 6.5, divided by the standard error. And for the z-score for the LCL would be the working lower control limit minus 6.5 divided by standard error. But my question is, how can I find the standard error? I need my standard error here. What is the formula for the standard error? The standard error equals to the standard deviation divided by under root of n. My sample size is 6, but I need my standard deviation. I need my standard deviation. Do we have anything? Do we have anything to find the standard deviation? Hmm? What was the formula for the R bar? The formula for the R bar is this, if you remember. The formula for the R bar is this. This is mentioned in your module. R bar E is also equals to sigma D2. So this is the formula. This is the formula. I know my R bar, now this is working R bar. I'm using my working R bar, the updated one, right? And that was 3.83. And I need my standard deviation. My standard deviation would be R bar minus D2. If I need my standard deviation, I can bring the D2 because it's multiplying on the right side. It'll get divided on the left side. So the formula would be R bar divided by D2. I can find the value of D2 by looking at this table. My sample size is 6. Now this is the small D2, right? And that is 2.534. Corresponding to 6, that is 2.534. So this is how you would get your standard deviation. 3.83 divided by 2.534. 2.534. Now divide that and get your standard deviation. 3.83 divided by 2.534 34, and you would get 1.51. You're getting 1.51. And I think this was 3.88. I have erased it, but whatever your updated working limit was, use that. Now, this 3.83 is the previous one. You have to use the updated one. And I believe that that was 3.88. Just like make sure that you're using the updated working hour bar, the updated one, after kicking out the sample, number 28. And this is happens to be 1.53 and not this one. 1.53. So this is your standard deviation. Now you can plug the value here to get the standard deviation. The standard error would be equals to 1.53 divided by the under root of 6. Divide this value by the under root of 6. You would get standard error of 0.62, 0.625, right? 0.625. Yes, the standard error is 0.625. Now you can find the z-score for the upper control limit. And what was your upper control limit? 7.43. Your working upper control limit, by the way. 7.43 minus 6.5 divided by 0.625. What would you get? 7.43 minus 6.5. Divide this value by 0.625. You're getting 1.488. So this is your z-score. And I'm finding the z-score for the lower control limit, but I told you that the probability for at this z-score would be approximately to zero. So you can actually negate the z-score for the lower control limit because your mean has went up. But I'm still finding the z-score for the lower control limit. And that would be, what was my lower control limit? 3.67. My lower control limit was 3.67 minus 6.5 divided by 0.25. And I would get 3.67 minus 6.5, 3.67 minus 6.5 divided by 0.625. So I'm getting minus, so minus 4.528 is like, if you draw this chart, your 99% of the data is within 3 standard deviation, but this is like 4 standard deviation. You cannot really expect any number like so far. So the probability of such a number is approximately zero. Because see, your 99% of the percentage of the data is within the limits of 3 standard deviation. This is like defined rule. If you go to the Google and you write in normal distribution, how much data falls into the 3 standard deviation limit? It's 99 point something. It's almost like 100%. It's a rare case that it's like almost impossible to have any point beyond the standard deviation of 3. And you're talking about to find the probability, which is like almost 4.5, standard deviation away from mean. And the probability would nearly equals to zero for this case. So that's why we negate this. And we are only, interested in the points which are 1.48 standard deviation, right? Now, what I can do is I can go back to my Z table, right? I can go back to my Z table, and this is 4 point. What I'll do is I'll first, in the first column, because I can't really, or what I can do is I can go my browser. Uh, But I'm pretty sure like you guys can now look the relevant relevant the value. You will go to the first column of x. X is basically your x bar or z score, and you will see where 1.4 is positive 1.4, and then you would go in the column of 0.08, right? So see where this is like corresponding, where this is intersecting. And whatever value you will get here, you will subtract it from 1. And that would give you your answer. And the answer for this was approximately 0.06, 0.06. And that would be almost what? It would be 1 minus 0.9313. Just like cross-check this value, and you would get 0.08687. So this is your probability, right? And this is and now to find the ARL, what would you do? Because I need my ARL. The formula for the ARL is 1 upon P. So 1 upon 0.0687 would give you almost 14.56. Now what is this number? These are the samples. Like you assigned a variation into your process, and it would take almost 14 samples to signal that change out, right? So this is what the ARL tells you. And the ATS would be the same number. And why? Because you're taking each day, right? So the ARL multiply by how often you're taking sample, you're taking after 1 day, right? So your ATS would be the same. You would get after, like, you will signal the change out after 14 days, almost like nearly 14 days or 15 days. Like 14.5 is actually would be considered as a 14 days. So this is all we will have to cover in this chapter, in this question. I try to touch upon like this is all the questions can be around this chapter. And I try to like, touch upon in every concept, and let's see how much it help you. And I'll try to record I'll try to record for every possible um, problem from each corresponding chapter. So I did for the statistical process control, and I'll do the same for maybe for the time series and for contingency tables. But I believe the contingency tables are pretty clear, right? But because we covered this chapter in the very start, and there was little like confusion, so I hope this video helps you a lot. Thank you.